Okay. Today our subject is again controlled Markov chains, and I would like to make a short review of what we have learned last time. We have the definition of a controlled Markov chain. The Markov chain that we are studying is a finite state, so it is represented by a transition probability matrix, which is an I by I matrix. And of course, we have to include the initial condition. I mean that the initial distribution of probabilities for the states, which is denoted by pi 0. If we have a control, this U usually belongs to some set, or R, or set of integers, or the set 1, 2, 3, etc. And it is called the input. If we have an input, then of course it must be used for some reason. And therefore, for the controlled Markov chain, we define an objective function that is a cost function that we have written as J, which is equal to the sum. K represents the time, K from 0 to n. So I'm talking about a finite horizon there. Some of the incremental costs, those CKs are called incremental costs. They need not be stationary. And it is a function of xk and uk. And of course, this is a random quantity. So we just take the expected value of that, say, cost to obtain, say, that the overall J value. Our aim is to minimize this J, minimize J. With respect to what? Of course, by selecting that UK for each K. K is usually a function. First of all, I'm sorry, xk belongs to the set 1 to I. So it is the set of states, and UK belongs to that feasible set U. And we have to specify what that UK is. We just say that UK is a function of, say, the past states. So we can write here that is as a function of x0 to xk. And now, however, for our case, we apply Markov policy, so that our UK is only a function of the last state. In other words, UK is equal to G sub k of xk. So that is the summary of what we have done. And then furthermore, we have written this expected value as a summation, term by term, and we just said that we can obtain the value of the objective function recursively with respect to a given G there. So if G is given to us, then we define this J as J super G. And let me write what G is. G sub K is G sub K of xk will be our input, which is equal to UK. And with this choice of, say, UK, I can write the overall objective function Jg as the expected value of C sub k of xk and G sub k of xk. And usually, a G is written here, but I will not do that in the rest of this time, to emphasize that this xk depends on the law that we have selected, and of course also the UK. So this is our Jg, and we would like to, I'm sorry, that is the summation, k from 0 to n. And we would like to evaluate this function recursively because it will help us in obtaining the optimal solution. The optimization of this function with respect to UK, or selection of this gk optimally, seems to be a little bit difficult, but however we will see that it is not. So we will apply backward recursion, and in the backward recursion we will define the concept of cost to go. Cost to go is something like that. This is the time horizon, let's say. That is the time k is equal to 0, and this is the final time k is equal to n. And I would like to change this k to L instead of using K, I will use L because of some reason. And I will assume that I will start from this point where L is equal to K. Okay? And the cost to go is the total cost obtained on that time interval, and it depends on the state at this time, in other words, xk. So we just write cost to go by using the letter V, and it will be, say, let us write it as Vk. It will depend on G, of course, and it will be a function of this xk here. Therefore, the aim is to calculate this Vkg recursively. Starting from the last time, I mean that first we will obtain Vng, and then we will obtain Vn minus 1g, and then finally we will obtain V0g, and we will obtain them for each xk, so that that will be equal to, okay, that will be equal to, depending on the state, V sub n g of state xn is equal to 1 up to V sub n g of the state xn is equal to I. So that actually, we will not calculate a single value there, but we will calculate a vector of size I. So maybe we can put it in the vector form and write it as this one, define this one as our Vng vector. Same thing is true for all the other V's, so that each V will have a size which is equal to I. And now, since our aim is to find them recursively, we will start from the final vector and obtain what this Vng is of x is equal to I, let's say. That is equal to, according to our definition, the expected value of the summation k from n to n of the expected value of c sub n of xn, gn of xn. But the computation of this expected value, given that xn is equal to I, because we assume that xn is equal to I. The computation of this expected value is so easy because it is a constant, and it is exactly equal to c sub n of I and gn of I. If V and G of xn is equal to I equal to that one, then we can quite easily write what V and G vector is. It's exactly equal to C sub n of 1 Gn of 1 when the state is 1, and it is equal to C sub n of capital I, which is the number of states there, G sub n of capital I, and that is obtained. So it's so easy to calculate V sub n for the last time, which is equal to n. And now I would like to calculate V n minus 1 g vector. To calculate this V n minus 1 g vector, let us assume, or let us obtain one component of it, and by writing xn minus 1 as I. So what does that mean? That means that we are here at the time n minus 1, and we are computing the cost to go for those two time steps. And we assume that at this time, we started from the state which is equal to I. And that is equal to, therefore, expected value of C sub n minus 1 of xn minus 1 and G sub n minus 1 of xn minus 1, and plus the last term C sub n of xn, G sub n of xn, given that xn minus 1 is equal to I. Okay. And now We will continue with this expression starting from the first term. The first term is so easy as before because that state is known at time n-1 and it is equal to I. So that when we are writing this v sub n-1 g, that xn is equal to xn-1 is equal to I, the first term is just c sub n-1 of I and gn-1 of I. The expected value is equal to itself, it is a constant. And now we have to write the second expected value there. The second expected value is the expected value of c sub n of xn and gn of xn, given that xn-1 is equal to I. Okay? The evaluation of this expected value is again not so difficult, so that overall expression is cn-1 of I, gn-1 of I, plus, okay, now for that one, I will write the value of this function for any value xn which is equal to j, g sub n of j, and then multiply it with the probability that xn is equal to j, given that xn-1 is equal to I, and take the summation over all possible j values, so that j will start from 1 to I. That's nice, because we know what that probability is. This is exactly equal to the ijth entry of the matrix PG. It is the ijth entry. So we can write the overall expression as cn-1 of I, gn-1 of I, plus, okay, in that sum, I would like to write it as a multiplication of a row vector with that of a column vector. And the row vector will be equal to pi1, pi2, these are the ijth elements of that one, pi capital I, multiplied by the column vector, multiplied by the column vector Cn of j is equal to 1, so that 1 gn of 1, and Cn of I, gn of I, capital I. Okay. Now, the second one, when we look at the second one, we just observe that this is nothing but our v sub n g vector that we have derived before. And then when we look at that one, we just see that this is the ith row of PG matrix. So we have multiplied the ith row with that v and g there. And we have to do this for all I, starting from I from 1 to for all states up to I. And as a result, we will obtain vn-1g as a vector, writing one after the other all those equations as a vector. We will obtain it as c sub n-1 of I, gn-1 of I, c sub n-1 of I'm sorry, this is 1, 1, 1, 1, capital I, g sub n-1 of capital I, plus, now we have the first row multiplied by that one, second row multiplied by this vector, etc. The overall summation or overall multiplication will give us a vector of this form. And actually, previously we have defined that one as our incremental cost vector at time n-1. This is again a vector of size I. And then at the end, we end up with a single formula that this, say, V sub n minus 1 G is equal to Cn minus 1 G, of course, that is okay. It depends on G, but I will not write it, plus Pg times V and G. This Cn minus 1 depends on G because that the second argument here is a function of G there. Okay, now we have obtained that expression. That is nice. That serves our purpose of obtaining, say, recursive expressions for those V's. But we have to go say that at time k, an arbitrary time k here. So for the arbitrary time k, I will rewrite the expression. We just write it as Vk G at time k, that is cost to go. Remember that it is the total cost of going from state k up to the final time. The equation here is in the recursive form. That is what we would like to obtain. But however, we have to apply it for an arbitrary k value. In other words, we have to calculate the cost to go for, say, or the vector vkg. And how to obtain that one? Let's say that xk is equal to I. Let us start with this thing as before. So that this is exactly equal to, according to our definition, the expected value of the summation L from k up to the time n of C sub k of xk, I'm sorry, C sub L of xl, gl of xl, given that xk is equal to I. So the aim is to calculate this cost to go. That is the cost starting from the state I at time k, and that is our definition. And again, I can write it as this one, as the expected value of the first term here is C sub k of xk, gk of xk, plus the others, that L will start from k plus 1 and will go up to n, C sub L of xl, gl of xl, given that xk is equal to I. Now, this given is for all of them. And now the first term is again easy because we know the value of xk. It is exactly equal to I. This is I. So that the first term is C sub k of I, gk of I, plus, now we are interested with the second term, and the second term is the expected value of that sum L starting from k plus 1 to n of C sub L of xl, gl of xl, and given that xk is equal to I. I would like to write the second term as a function of vk plus 1. Unfortunately, I cannot call it directly vk plus 1 because at the given condition is not at time k plus 1, but it is at time k, where the starting time for this term is k plus 1. So what we do for let us call the second term as the term A, and we can write the A as the expected value of, now I will write that one as the expected value of the summation L from k plus 1 up to n C sub L of xl, gl of xl, given that, now I will put here an extra given condition, that is xk plus 1, and also xk is equal to I. But of course, when we do that, in order to obtain the same expectation, we have to take one more expectation. It is the expectation when xk is equal to I. Okay, so we can write the overall expression in this way. And now, when we look at that one, since our process is a Markov process, the information given to us here as xk is equal to I does not affect the result. And we can just reduce it to the expected value of the inner expectation as the, up to here, as the expected value of that summation L from k plus 1 up to n C sub L of xl GL of xl, given that xk plus 1. Since we have used Markov policy, we can do that. And the outer expectation is to take the expected value of this whole thing with the given condition that xk is equal to I. We are very happy with this expression because now that the first term is just the definition of our vk plus 1, but however, vk plus 1g, but however, the state value is not given to us. It is left as a random quantity, so that the whole thing is a random quantity, which is a function of xk plus 1. And then finally, when continuing with A will be written as the expected value of vk plus 1g of xk plus 1, again a function of g, given that xk is equal to I. Now the computation of this expectation is not difficult because that this is equal to the value of vk plus 1g when xk plus 1 is equal to j multiplied by the probability that xk plus 1 is equal to j, but we have the given condition and xk is equal to I. Okay? Of course, we have to take the sum over all possible values of j starting from 1 to capital I. Now, let's see what that thing is. We have already seen this expression. It will be exactly equal to Pi1, Pi2, these are g dependent all, multiplied by Vk plus 1g of 1, Vk plus 1g of I. Again, this is the ith row of Pg, and this is our Vk plus 1g vector. So the overall recursive expression can be written as Vkg in the vector form is equal to, the first term here for each I can be put into the vector form once more, and it is denoted by Ckg, the incremental costs. And finally we have here Pg, even that may depend on k. Why? Because g depends on k, multiplied by Vk plus 1g. And this is the desired, say, recursive expression, starting from the final condition that Vng is just Cng. And once we obtain, say, that all those terms, then we get Jg as pi 0, which is the initial state distribution, multiplied by V0g. So we can recursively calculate all those v's up to the time g, and then afterwards say that obtain this result as the value of our objective function. Now I would like to give you a simple example related with that problem. example. In the example, we have a three-state machine, three-state Markov, controlled Markov chain. We have those kind of transition probabilities non-zero, and the others are something like that. And therefore, we have a P of U matrix. These are all dependent. For example, this is P11U, this is P12U, etc. They all depend on U in our example. And U is selected as a member of the set 0 and 1. So that is our capital U set, feasible set of all inputs. We have two inputs only for that one. Okay, we changed that one a little bit. We have our P of U, which is equal to P11U, P12U, no transition from 1 to 3, so we have a 0 there. No transition from 2 to 1, and we have P22U and P23U. And we have only one transition from 3 to 1, so I have 1, 0, 0 as the last row of this thing. We have to specify our P of 1, U is equal to 0, or P of 0. That is, I mean that the value of P11U should be given to us to complete the problem. And we just assume that this is equal to 0.8 when U is equal to 0, 0.2 and 0. And the second line is 0, 0.6 and 0.4. And the last one is 1, 0, 0. That is our P of U when U is equal to 0. And P of U is equal to 1 is equal to, that is also given to us, is equal to 0.4, 0.6, and 0. 0, 0.6, and 0.4, and 1, 0, 0 as before. Now, the problem is not completely specified yet. We have to write what pi 0 is. Let us say that this is 1, 0, 0. And still we don't know what the objective function is. We have written the objective function as j of g, which is the expected value of the sum. The final time selected in this problem, or given in this problem, is 3. So that we will go starting from k is equal to 0 up to 3. And the incremental costs are stationary. I mean that they do not change with time. And they are functions of xk and uk. So that we would like to, say, obtain the value of the objective function for that problem. But however, policy should be also given to us. The Markov policy tells us that each uk will be equal to, or g of xk, and it will be equal to, uk is selected, so that g of 1 is selected as 0. We have 3 values for xk. G of 2 is selected as it is selected as 1, and g of 3 is selected as 1. First of all, we do not claim that this is the optimal policy. To talk about the value of the objective function, of course, objective function must also be known, and the objective function, which is the, although given here, incremental costs should be specified. C of xk uk is selected as the absolute value of 3 minus xk. No need for the absolute value, but however, it is given in this way, plus u. Okay. So this is the incremental cost. Now the problem is completely specified. Let me say again that the selection of this policy is, of course, cannot be claimed as optimal or anything like that, but the aim is to calculate, say, the value of the objective function for that policy. This is our aim, and we will do it recursively. The first step in this recursive computation is, of course, obtaining the matrix PG. Since G is given to us here as that G of 1 is equal to 0. So if we are in the first state, we will use this part of our P vector. In other words, when U is equal to 0, we will use, say that transition probabilities will be equal to that one. So it will be 0.8, 0.2, and 0. When U is equal to, when state is equal to 2, U should be selected as 1. So we go to the second matrix here and choose that thing as our line, second line. That is 0.0, 0.6, and 0.4. And when say that the state is equal to 3, this is really not important, but it will give it will have an effect on the cost, but it is selected as again 1, so that we have to use the third line from this second matrix here. Therefore, this is 1, 0, 0. I also have to calculate our C. I will not write here K because it is not a function of time, but I will write CG. CG will be equal to, we just look at, say that this incremental cost there. If the state is 1, then U is equal to 0. When this is 1, then the corresponding U is equal to 0. If the state is equal to 2, the corresponding U is 1. If the state is equal to 3, then the corresponding U is again 1. That is our rule. So when we calculate the incremental cost, when state is equal to 1, it will be equal to 3 minus 1 plus 0. So this is 3 minus 1 plus 0. When state is equal to 2, I have to use the input as 1 there. So when state is equal to 2, we have 3 minus 2 plus 1. That is 3 minus 2 plus 1. And when we're looking to the last state, this is 3 minus 3 is 0, but the input is equal to 1. So we have another 1 there. As we have obtained this PG from our P0 and P1 matrices, like that one, we have obtained this CG from the given, say, 2 different C vectors maybe. Okay, so that will be equal to 2, 2, and 1. Now, the rest is quite easy because we have derived all the formulas, and we can write V3G, since our final time is equal to 3, as, maybe I should better write C and G, but however this is CG because for each time we have exactly the same vector, and this is exactly equal to 2, 2, and 1. We can obtain V2G, that is equal to C2G plus PG multiplied by V3G. In other words, this is again the same thing, 2, 2, 1, plus our PG matrix, which is written here, 0.8, 0.2, 0, 0, 0.6, 0.4, and 1, 0, 0, multiplied by 2, 2, 1. Very simple computation will give us the result. 4, 3.8, and 3. Okay. So we found the value of V2 vector. Now we are going backwards recursively. The next step is to calculate the V1 vector. But now we all know what to do. It's easy. We know that V1G will be equal to C once more plus PG times V2. That is 221 plus the same P, 0.8, 0.2, 0, 0, 0.6, 0.4, 100. Now it is multiplied by not 221, but 4, 3.8, and 3. The new result is something approximately 655. Finally, we will obtain V0G as CG plus PG multiplied by V1G, and exactly the same thing, so that I will not write it again. I will just write the result, and this is approximately equal to 7.5 and 6.5 and 7. Okay, since our initial state distribution pi 0 is given to us as 100, JG, the overall objective value, will be equal to 100 multiplied by this V0G, which is equal to 7.5 here. Okay, that will be all for this session. And we have now studied how to obtain recursively the value of the objective function. And for that purpose, we have defined cost to go. And the recursion here is in the backward direction.